Good morning, everyone. I warmly welcome everyone to the third lecture of STEM's 2022 Qualifier Camp. Today, we are quite happy to have Professor Akshayaram Srinivasan with us. Let me start with a brief introduction about him. Professor Srinivasan is a faculty at the School of Technology and Computer Science, TIFR, Mumbai. His research interests are broadly in cryptography and particularly in multi-party computations and also several other areas of cryptography. He completed his PhD at the prestigious UC Berkeley under the guidance of Professor Sanjam Garg. Today, he will be talking on a very exciting topic and introducing to all of you the secure multi-party computations, which has broad applications in practical life and in a lot of other places in theoretical computer science. Before we begin, just a quick instruction. If you have any questions, please feel free to put them in the chat or raise your hand, or you can also unmute yourself and directly ask the professor. If you put in the questions in the chat, the moderators will voice them at the appropriate time. Without further delay, I invite Professor Srinivasan to give the talk. I hope all of you enjoyed that.
Thank you so much, Amik, for the introduction. So I'm really excited to meet you all virtually and share some of my learnings about secret sharing and secure computation. Okay, so let's begin. Okay, so let's consider this following scenario. So let's say that there are three friends, P1, P2, and P3. Okay, so all these three friends decide to go for a movie. So P1 has a bit B, which indicates whether he will be going for the movie or not. That is, if B is equal to 1, then let's say that P1 will be going for the movie. If B equal to 0, then P1 will not go for the movie. If he doesn't go for the movie and let's say he informs one of his friends, say P2, about his choice, then P2 might back out of the plan, leaving P3 stranded. Okay, so P1 wants to ensure that even if he doesn't want to, or even if he doesn't go for the movie, P2 and P3 should go for the movie and enjoy it. So he's a good friend in the truest sense. Okay, so what he does is that he sends two bits, B2 and B3, respectively to P2 and P3. And the distribution of these two bits, B2 and B3, has the following property. So individually, that is the marginal distribution of B2 and the marginal distribution of B3 doesn't give any information about P1's choice. That is, if just using the bit B2 that P2 received from P1, P2 does not know whether P1 will be going for the movie or not. Similarly, using the bit B3 that P3 received from P1, P3 cannot determine whether P1 will be going for the movie or not. In other words, the marginal distribution of B2 and B3 gives no information about the bit B. But what does P1 want to ensure? That if P2 and P3 come together, then the joint distribution of B2 and B3 should reveal should reveal B. Okay, so this is the basis of secret sharing, meaning that if I only get one of the two shares, so B is split into two shares here, meaning B2 and B3 are the respective shares. So just given one of these two shares, no information about the bit B which is being shared is revealed. But given both the shares, you should be able to reconstruct what B is. Okay, so this is what is called as a 2 out of 2 secret sharing. So how can we achieve such a secret sharing scheme? This is fairly straightforward. So what do we set? So we set B2 to be a random bit chosen uniformly from 0 1. Okay, so you just flip a coin, if it is heads, say set B2 to be 1, if it was tail, set B2 to be 0. And what should B3 be? So B3 is just B2 XOR with B. Okay. So does this construction satisfy both the properties that we want? Let's see if it does. Okay. So what is the first property? The first property is that given only B2 or given only B3, we should learn no information about the underlying choice bit. Okay. So let's see whether this construction satisfies this property. So let's start with B2. So how is B2 distributed? B2 is just distributed as a random bit. That is, it's independent of B, right? So the marginal distribution of B2 reveals no information about B. So let's see whether B3 could reveal any information. So what is B3? How is it distributed? B3 is just said to be B2 XOR with B. But how is B2 distributed? B2 is just chosen as a random bit, right? So if B2 is chosen as a random bit, what can you say about the distribution of B2 XOR with B? It's again a random bit, right? So the probability that B2 XOR with B is 0 will be half, and probability that B2 XOR with B is 1 will again be half. So this is again a random bit, and hence this reveals no information about B. Okay, so but what about the second property that we want to ensure? That given both the bits B2 and B3, we should be able to get back B. So how do we do this? So given B2 and B3, how can we retrieve B from it? You just XOR B2 with B3, and that result will be B. Right? So this is one of the fundamental cryptographic primitives, and this toy example is a special case of 2 out of 2 secret sharing, meaning that I need both the shares in order to reconstruct the secret, but given one of the shares, you get no information about the secret. Okay, any questions about this before we proceed? Okay. Okay, so what we just saw was a 2 out of 2 secret sharing, meaning that the secret was split into 2 shares, B1, B2 and B3 in the previous case. So now a natural generalization of 2 out of 2 is to that of n out of n. Okay, so let's say that I have a, okay, so there is a question. Okay, so how is B2 XOR with B3 equal to B? Okay, good. So what is B3 here? So B3 is just B2 XOR with B, right? If I just XOR with B2 on both sides, I'll get B2 XOR B3 to be equal to B. Okay, so okay, so are there any other questions? So can you monitor the chats and let me know if there are questions, Amit or Anil?
Yeah, sure.
Okay. Okay. So the previous case was that of 2 out of 2. So natural generalization is that of n out of n. So what is this setting? Okay. So let's say P1 again has some bit B, and here, P1. Okay. So there is a question about XOR operation, right? Okay. So XOR is just a bit operation that acts on 2 bits. Let's say X and Y, and it has the following truth table, right? So if X and Y are both 0, 0, then the output of XOR is just 0. If it was 0, 1, it is 1. If it is 1, 0, it is 1. And if it is 1, 1, then it is 0. So if both the bits are same, the output of the XOR is 0. Otherwise, the output of the XOR is 1. Okay, so it's a fundamental gate. Okay. Okay. So coming back to the case of n out of n secret sharing. So P1 again has a bit B, and he wants to split this bit into n shares, B1, B2, B3, up to Bn, for some n which might be greater than or equal to 2. So in the previous case, we considered the setting where n was 2, but n could be much larger. Okay, so again, we need two properties. The first property is that given P1, B2 up to Bn, you should be able to recover B. Right? Just like in the case of 2 out of 2, that is if you had both the shares B2 and B3 that was given in the previous slide, you should be able to recover B. But for any set of 1 to n of size at most n minus 1. That is, if you are missing even a single share, that is, you can consider an arbitrary set of size at most n minus 1. That is, you should not include at least one of the shares. Then let's consider the set S of 1 to n of size at most n minus 1. Then if you are given Bi for all I in S, then this joint distribution of all these Bis reveals no information about B. That is, you can think of all these bits to be uniformly distributed. So in the previous case, what we did was that we proved that B2 and B3 are just randomly distributed. That is, marginally, their distributions are just random, but taken together, they reveal B. So similarly, you can think of, for any set S of size at most n minus 1, the shares corresponding to that set is just random. So essentially, since it's just random, it reveals no information about B. Okay, so how do we construct such n out of n secret sharing? Just extending the case of 2 out of 2. Okay, so let's just start with special case of n equal to 3. Okay, so what do we want? So we want to split B into B1, B2, and B3 such that any two shares amongst 1, 2, 3 reveals no information about B. But if you take all the 3 shares, then you should be able to reconstruct. So how do we do this? Any ideas?
So there's a suggestion in the chat box saying XOR all the bits.
Right. So yeah, and an actual suggestion is to just XOR all the bits to recover B. But how should the bits be chosen? That's the important part. So can you tell how should B1, B2, and B3 be chosen?
So there's another suggestion, like individually in order. First choose B1 and then B2 and so on.
How do you choose B1 and B2? From what distribution? So what did we do in the previous thing? How did we choose B2 first? In the case of 2 out of 2. So we wanted to split to B2 and B3. So how did we split? Yeah, B2.
Randomly.
Yeah. So can you naturally generalize this to 3 out of 3? Okay, so I see one of the suggestions.
So one suggestion is B2 is B1 XOR B and B3 is B2 XOR
so let's
B1.
just teaser that suggestion. Let's see what. Okay, so B1, let's say it's chosen randomly from 0, 1. Okay, so I'm just indicating this left arrow to mean that I'm sampling uniformly from that set. Okay, so this is some notation that I'll be using. So now the suggestion is to just set B2 to be B1 XOR with B, even for the case of 3 out of 3. Okay. Okay, so let's just ignore B3 for a moment. So how do you recover? So given B2, B1, B2, and B3, you can just recover from just using B1 and B2, right? Because you can just XOR these two to get back B. But does it satisfy the second property, meaning that for any set S of size at most n minus 1, the joint distribution of Bi for I in S reveals no information about B? It does not, right? So if you consider the set 1, 2, that's S to be 1, 2, then it has size 2, which is n minus 1. N is 3 here. But given B1 and B2, you can recover B completely, right? So this does not satisfy this required property. Okay, so what you do is, instead of sampling B2 has B1 XOR with B as in the previous setting, what you do is to sample B2 also uniformly from 0, 1. And what you do is to set B3 to be B1 XOR B2 XOR B. Okay.
So there's one question in the chat about the second property, that no smaller set can reveal the information. Can you just explain it once again?
Okay, so revealing no information about B is a bit hard to formalize for now, but think of the case where for any set S of size at most n minus 1, the distribution of Bi for I in S should be uniformly distributed. It should be a set of size of S random bits. I'll formalize what it exactly means to reveal no information about B in the next couple of slides. Think of it as uniformly distributed, those bits corresponding to the set S. Okay, so now, so this is the case of 3 out of 3, and you can actually easily verify that this satisfies both the properties. Namely, if you're given all the 3 bits, you just XOR them together to get back B. And you can also prove that given any 2 of these bits, no information about B is revealed. In other words, any 2 of these bits are just uniformly distributed. Okay, so now how do you generalize it to the general N? Any N? Any ideas? Yeah, it's the same, right? So you just have n shares B1, B2 up to Bn. So you just sample the first n minus 1 shares uniformly and set the nth one to be B XOR B1 XOR B2 to Bn minus 1. Okay, so given all the n shares, you can actually reconstruct B, but given any n minus 1 shares, those are just randomly distributed and no information about B is okay, so this is this first non-trivial extension that we saw from 2 out of 2 to general n out of n. Okay, so let's try to generalize it even more to the case of what is called as threshold secret sharing. Okay, so what do you have? You have some secret S. Okay, so you want to generate n shares S1 to Sn as before, but instead of requiring all the shares in order to reconstruct the secret, let's say you just need t plus 1 of the shares to reconstruct. Meaning that if you are given any set K, which is a subset of 1 to n, and size of K is at least t plus 1, right? Then given Si I in K, you should be able to reconstruct and get back S. But what about the secrecy property that we saw? So in the previous case, you wanted to show that any n-1 shares reveal no information about the secret, right? But here you cannot say the same thing, because you should be you are allowed to reconstruct the secret from any t+1 shares. So what you want to show that if there is any k prime of 1 to n, which is of size at most t, then Si for I in k prime reveals no information about the secret S. Okay, so the important property that we want to satisfy is that this does not hold for for a particular set K of size t+1. You should hold for any set K of size at least t+1. That is, given any arbitrary subset of n of size at least t+1, you should be able to reconstruct the secret. Similarly, the second property requires that if you are given at most t shares, then no information about the secret is revealed. It should hold for any set of t shares, not just for some particular set. Okay, so there is a sharp threshold at t, right? So if you are given at most t shares, no information about secret is revealed. But even if you are given one additional share, that is, if you are given t+1 shares, everything about the secret is revealed. That is, you can reconstruct the entire secret. So that's why it's called as a threshold secret share. Okay, so think of this SIs as for any k prime to be uniformly distributed. So that's the requirement. Any questions? So I think there was a question on chat.
No, there are no questions.
Okay, so okay, so what's the formal definition? So a t+1 out of n threshold secret sharing has the following properties. The first is, of course, the correctness. It says that any set of t+1 shares can be used to reconstruct the secret. Okay, and for security, we require that for any two secrets S0, S1, and for any set T of size at most this threshold T, if you consider the shares that you corresponding to the set T that you obtain when you secret share S0, and you consider the shares that you obtain when you secret share S1, these two distribution of shares are identical. Okay, think of these two distributions to be just uniform distributions on T values, where the values correspond to the shares. Okay, so since for any two secrets, the shares corresponding to any set T of size at most small t is identically distributed, it just follows naturally that the shares of any set of any set of T shares reveals no information about the secret. Okay, so this is the formal definition, but even if you are not able to fully follow it, it's okay. So just intuitively understand it to be the case where the set of any T shares are just uniformly distributed. So this is something that will satisfy, but it's not necessary. Okay, so is there a question?
So there's one question. Can you just repeat the definition, the formal definition once again?
So correctness is something that we already discussed, that any set of t plus 1 shares can be used to reconstruct the secret. And for security, we require that for any two secrets S0 and S1, okay, the shares of corresponding to the set T of size at most small t, okay, the set of shares that you generate while sharing the secret S0 and the set of shares that you generate while sharing the secret S1, these two distributions are identical. Okay, so this is the secrecy property. Okay, so are all of you familiar with the notation ZP for some prime P? Or should I explain it again?
Maybe a quick brush would help.
Yeah, okay. Okay, so ZP is the set 0, 1 up to P minus 1. Okay, and it has the associated plus and multiplication operations. Okay, so if I have two elements A comma B in ZP, then A plus B mod P is another element in ZP. So this is what I call as plus over ZP. And of course, the product A comma B in ZP, if I want to take the product, it's just again, just reduce this modulo P. Okay, so it's again an element in ZP. So plus and product map two elements from ZP to another element in ZP. Okay, so and ZP also has the additive and multiplicative inverse. So for any A, there exists a B such that A plus B is 0. Again, modulo P, which is just B is just minus A mod P. Okay, and again, for any non-zero element, since P is prime, so I should have mentioned it, P is a prime. So there is A, for any A, which is not equal to 0, there is A inverse such that A times A inverse is 1 modulo P. Okay, so in other words, ZP is a finite field. That's what I wanted to say. So yeah, people might not be familiar with finite fields, so I wanted to take a concrete example. Okay, so polynomials. Okay, so a polynomial P over some variable x over ZP is defined to of degree D is a polynomial of the form A0 plus A1x plus A2x squared up to AD x to the D, where A0, A1 and AD are all in ZP. Okay, so this is a polynomial over ZP. Okay, so now, so let's see how to construct a threshold secret sharing for any T. That is, let's see how to consider a T plus 1 out of N secret sharing scheme. Okay, so recall that it has to satisfy correctness and secrecy. Correctness requires that any T plus 1 share should be are enough to reconstruct the secret. Secrecy requires that any set of T shares reveals no information about the secret. Okay, so these are the two properties that one needs to satisfy. Okay, so let's say S belongs to ZP for some prime P, and P such that P is greater than N. That is, we want to construct a T plus 1 out of N. We choose a prime P and we consider some secret S that is in ZP, and P should be greater than N. Okay, so let alpha 1, alpha 2 up to alpha N be distinct non-zero elements in ZP. It could be arbitrary elements. The only thing that you need to satisfy is that they all needs to be distinct and they are all not zero. Okay, so so let alpha 1 to alpha N be distinct non-zero elements in ZP. Okay, so let's see how to split the share into N shares S1 to Sn such that it satisfies both correctness and secrecy. Okay, so this is the share algorithm. Okay, so that takes as input the secret that you want to split. And what it does is the following. So it chooses R1 to RT uniformly from ZP. Okay, it chooses T elements. Recall that we want to ensure a T plus 1 out of n secret sharing. Okay, so what share algorithm does is that it chooses T elements R1 up to RT uniformly from ZP. Okay, so each of them is sampled uniformly and independent. Okay, so the second step is that it defines a polynomial P of x of degree T such that the coefficients of x to the T is RT, x to the T minus 1 is R to the T minus 1, up to R1x. And what about the constant term? It's actually the secret that you want to share. Okay, so you choose T elements uniformly, define a degree T polynomial where the chosen elements are the coefficients of x, x squared, x cube up to x to the T. And the secret that you want to share is your constant term. Okay, so now what are the shares S1 up to Sn? So S1 is just the evaluation of the polynomial at alpha 1. S2 is evaluation of polynomial at alpha 2, and Sn is the evaluation of polynomial at alpha. Okay, so these are the shares that you want to send. Okay, so is the sharing clear? Okay. So now, how do you reconstruct? So what do you want to say? So you are given some set T of size at least T plus 1, and you are given the shares Si corresponding to this set T. And you want to reconstruct S from these shares. How do you do this? Are there any suggestions on chat?
I guess not.
Okay.
Maybe you can explain it.
Okay. So what is the degree of this polynomial P? It's polynomial P. What is it? It's T, right? So from your high school mathematics, how many distinct evaluations are needed in order to uniquely determine a polynomial? It's actually
T.
It's actually T plus 1, right? So it's degree T polynomial. So you need at least T plus 1 evaluations in order to uniquely determine it. Okay, so what are the shares actually? So the shares correspond to the evaluations of these polynomials at distinct points, right? So given T plus 1 shares, you can just use Lagrange's interpolation in order to reconstruct. So use Lagrange's interpolation to reconstruct the polynomial. And once you reconstruct the polynomial, then the only thing that the secret is just the constant term, right? So you just output the constant term of this polynomial, and that's it. That's how you reconstruct. So given any T plus 1 shares, you have T plus 1 evaluations of the polynomial at distinct points. So all that you need to do is to just use Lagrange interpolation in order to reconstruct. Okay, so this satisfies the correctness property, meaning that any set of T plus 1 shares should be able to would allow you to reconstruct the secret. Okay, so what about the secrecy property? So what do you want to show? So if T is a subset of 1 to n of size at most T, we want to show that Si I in T reveals no info about S. Or in other words, Si are just uniformly distributed. So how do you show this? So how are these polynomial, how are these shares generated? It's just the evaluation at alpha 1, alpha 2 up to alpha, right? So in linear algebraic terms, so if I denote this polynomial, the coefficients of this polynomial as this vector S R1, R2 up to RT. So this is the polynomial in its coefficient formulation. So then what do I do? So if I just multiply with alpha 1 square, alpha 1 cube up to alpha 1 t, then what is the inner product of this with this? It's just p of alpha 1 with this s1. Right? So how do you generate p of alpha 2? You just left multiply with alpha 1, alpha 2, alpha 2 squared up to alpha to the t, and you get p of alpha 2, which is s2, and so on. So to get p of alpha n, you just multiply with this. Okay, so do you recognize what this matrix is? It's a special matrix. Yeah, it's the van der Waals matrix. And one useful property of van der Waals matrix is that its rank is t plus 1. Okay, so any set of t rows, any set of t plus 1 rows are linearly independent. Okay, so what are the shares? Okay, so now consider some t which is just I1 up to IT, where I1, I2, I3 are just elements, are just some numbers from 1 to n. Okay.
So there is suggestion, and there's an answer in the chat regarding the secrecy. So the suggestion is set P0 arbitrarily and use Lagrange interpolation again, and any secret could have given this.
Sorry, I didn't get what the suggestion was.
So the suggestion was set P0 arbitrarily,
okay,
and use Lagrange interpolation again, and any secret could have given this.
Oh, for proving the secrecy property,
Yes.
right? Exactly. That's what I'm going to do. So if you just choose T to be just I1 to IT, then the set of shares that correspond to the set T is just you just choose the rows of this van der Waals matrix corresponding to the set T. So this is just 1 alpha I1 squared to alpha I1 to the t, and so on. So 1 alpha IT squared to alpha IT to the power t, and you just multiply it with this coefficient vector. So these t rows are just linearly independent, right? Because the rank of van der Waals matrix is t plus 1. So what you do is that so how are R1 to RT just generated? These are just chosen uniformly at random, right? So what you can show by just basic linear algebra, that if you choose t arbitrary elements and you just consider random some linearly independent combination of those t elements, then each of those linearly independent combinations will be just uniform. Okay, so this just shows that p of alpha I1 up to P of alpha I T are just uniformly distributed. Okay, so this is just a basic exercise for you to try. So the exercise tells you that if you just choose T elements uniformly and you just consider some K combinations of them for some K less than or equal to T, and all these K linear combinations are all random, are linearly independent, then each of these K combinations is going to be uniform. So yeah, so using this, what you can ensure that since each of these linear combinations are going to be linearly independent, the evaluations of the polynomials are going to be just uniform. Okay, so this is how you show secrecy. Any questions so far regarding this threshold secret sharing or N out of N secret sharing?
So I was just wondering, so here you used polynomials to construct this. Like, are there any other objects with some
Yeah, so
combinatorial
actually
objects?
you can use any linear code to construct a threshold secret sharing. If you are familiar with coding theory, you don't have to necessarily use polynomial. But in fact, if you have observed, this polynomial based secret sharing is just read Solomon codes. Yeah, in fact, any linear code will give you a threshold secret sharing.
And any, like, are there any combinatorial objects maybe? I'm wondering.
Yeah, in fact, you can show that if the threshold T that you want to construct for is just constant, then objects called as perfect hash functions, I don't know whether you have heard about them. So these are purely combinatorial objects. So those can be used to construct a threshold secret share. But the problem is that if T becomes larger and larger, then the share size just grows exponentially. So as long as T is just constant or even logarithmic in N, the share size is just polynomial. Yeah, these are great questions. Any other questions? Okay.
I think you can continue.
Yeah. So let me just state a couple of useful properties of So the secret sharing that I just mentioned is Shamir secret sharing due to Adi Shamir from 1979. So Adi Shamir is the S of RSA encryption scheme. So let me state a couple of useful properties of Shamir secret sharing that will be used to construct a secure computation protocol later. Okay, so let's say that I have a secret S0. Okay, and let's say that I have the shares S1 up to Sn, which are just a T plus 1 out of N secret sharing of S0. Okay, so let's say I have another secret T0. Okay, and let's say T1 up to Tn are again a T plus 1 out of N secret sharing of T0. So what can you say about S1 plus T1, S2 plus T2 up to Sn plus Tn? If I just add the corresponding shares together, what can you say about this?
They will form a new secret sharing.
Of which value?
S0 plus T0.
Yeah, this is actually a T plus 1 out of N secret sharing of S0 plus T0. You see why it is the case? Okay, let me explain. So how is the secret sharing of S0 generated? You choose some polynomial P from some distribution, right? You just choose the higher order coefficients to be uniform and just take the constant term to be S0, and you just generate the shares S1 to Sn as just the evaluations of this polynomial at this polynomial at alpha 1, alpha 2 up to alpha n. Similarly, how do you generate shares of T0? You just choose another polynomial Q and just and then generate the shares as evaluations of the polynomial at alpha 1, alpha 2 up to alpha n. Right? So what happens if you just add these two shares? You'll get the evaluations of the polynomial P plus Q at alpha 1, alpha 2 up to alpha n. Right? And what is the constant? What is the degree of P plus Q? It's at most T. Right? And what can you say about the constant term of P plus Q? It's just S0 plus T0. Right? So this is actually a T plus 1 out of n secret sharing of S0 plus T0. Okay, so this is going to be extremely useful later. Okay, so let me give you another property. Okay, so let's again consider sharing of S0 and T0. Let's call the shares of S0 to be S1 to Sn, shares of T0 to be T1 to Tn. What can you say about S1 T1, S2 T2 up to Sn Tn?
So there's an answer in the chat saying the secret share for S0 T0.
Good, but is the threshold the same? That is, does it give a T plus 1 out of n secret sharing of it's not T0?
The answer is 2T. It will be a 2T.
Exactly. So it actually gives you a 2T plus 1 out of n secret sharing of S0 and T0. Why? Because these are evaluations of the polynomial P times Q at alpha 1 to alpha n. Okay. But what is the degree of polynomial P times Q? It's at most 2T, because each polynomial P and Q has degree at most T. So P times Q is going to be degree at most 2T. Okay, so it does not directly give you a T plus 1 out of n, but it gives you a 2T plus 1 out of n secret sharing of S0 T0. Okay, so this property is again going to be useful later. Okay, so just remember these two properties. Okay, so let me just summarize. So if you just add the shares, you again get a sharing of S0 plus T0 with the same threshold. Okay, if you multiply the shares, you get this sharing of S0 times T0, but with a larger threshold. That is, you double the threshold. Okay, so these two properties are going to be useful. Okay, so now we are done with secret sharing for now. So let's go into secure computation. So let me motivate secure computation. Okay, so let's say there is a user P1. Okay, he has some secret data. Yes. Okay. So he wants to store this data on the cloud. But clouds could be hacked, because we have seen many breaches on clouds wherein attackers could access all the files that are being stored. Okay, so P1 doesn't want to store this data on a single cloud, because single cloud could get hacked because we have seen many instances. So what he does is the following, right? So he chooses n cloud service providers, C1 up to Cn. And instead of storing the same data S on each of the cloud service providers, what he does is that he just secret shares this data into S1 to Sn using a T+1 out of n secret sharing scheme, and stores the corresponding shares on the cloud. So what does this ensure? So this ensures that even if T cloud service providers get hacked and the shares that are stored on these cloud service providers are revealed in its entirety to the attacker, then the secrecy property of the threshold secret sharing ensures that the secret of this user is still safe. That is, no information about the secret is revealed. So only under the case that T+1 or more cloud service providers get hacked, the secret could get revealed. But the probability of that happening, let's say it's very small. Okay, so a natural application of secret sharing is to split your data into multiple shares, so that even if some of the shares get revealed to an attacker, the secrecy of this data is still preserved. Okay, so this works great as long as your data is just statically stored on the cloud. That is, let's say that you have some secret data, you just store it on the cloud. Every time you want to retrieve the data, you just contact T+1 cloud service providers to send the shares, retrieve it, and so on. But in most of the instances, the data is just not stored statically. Right? Think of the instance where your secret data consists of your entire photo library from your mobile phone. And let's say at a later point of time, you want to search for some particular image. Let's say that the image that was taken from your phone on a particular location on a particular date. What do? The cloud service providers do not have access to your data in the clear, right? Because that's the whole point of secret sharing. Right? How can you retrieve the particular photo that you are interested in without the cloud service providers learning your actual photos? That's the whole point of you secret sharing your data. How can you do this? So one trivial solution is for the cloud service providers to just send whatever that they store to you, that you retrieve your entire photo library, and you can just locally in your computer just choose the data that you're searching for. But this is going to be extremely expensive, right? Because for every time you want to search for some photo, you are going to download the entire photo library from the cloud. So think about the bandwidth that you're going to spend on this for this purpose. Right? So can you ensure that for any secret data that you store, let's say that there is some function f that you want to compute on that data. Think about this function as being the search function that you have just described. That is searching for a particular photo that was taken on a particular day. Right? So what you do is just to send the description of these functions to this cloud. The clouds could just interact with each other using some protocol. And let's say that they send a short message that just grows with the particular output of the function that you're interested in. And you can just retrieve the function's output from this message that was sent back to the cloud. This is the goal of secure computation. So secure computation allows you to compute any function on the secret shared data that was stored on the clouds, while ensuring that the clouds do not learn anything about the data nor the output of the function that you are interested in. Okay, so the only thing that they learn is some function that you want to search, that you are interested in computing, but everything else about the secret data that was stored or the output of the function on that data is hidden from the cloud. Okay, so this is the goal of secure computation. Okay, so let me give you the formal definition. Okay, so for this purpose, so once the cloud service providers get a description of this function, they run some protocol between them. By protocol, I mean that they could send some messages to each other, process the messages, that is compute some functions on them, send some more messages and so on. So this is what is meant by a protocol, right? So a protocol pi is said to securely compute a function f against T server corruptions. Okay, so if the output, if it satisfies the following properties. Okay, so what are the properties? The first is, of course, the correctness property, meaning that the output of this client mean the one who stores the data on the cloud. So this is the client, these are the servers. Okay, so the output of the client at the end of the protocol is the function f applied on the secret shared data. So let's say that instead of just storing a single data, let's say that the client is storing n data points. Okay, so n is getting overloaded. So let's say m data points x1 to xm, some secret x1 to xm. It's being stored on n cloud service providers. So what you want to ensure is that the output of this protocol, output of the client at the end of the protocol is f applied on the secret on the data x1 up to x. Okay, what do you want for security? The view of any T servers is independent of x1 up to xm. Okay, what do I mean by view? So the view is whatever that the cloud service providers might see during the protocol execution. It includes the shares that was sent to them. It includes all the messages that they could receive from the other cloud service providers. And it also includes all the messages that they send to the other cloud service providers. So view is the entire thing that happens during the protocol execution. So view of a cloud service provider is whatever it sees during the protocol execution. Messages it sends, messages it receives, as well as the share that it received from the client in the first place. Okay, so for security, we require that the view of any T servers to be independent of x1 to x, meaning that the cloud service providers do not learn anything about the underlying shared data. And what about the efficiency? So as I mentioned, that cloud service providers could just send messages with each other. At the end of the protocol, they just send a single message over to the client who can use it to retrieve the output of the function. Okay, so the size of this last round message from the servers to the client is just grows with the output of the function on the data. Otherwise, what the cloud service providers could do is just send the entire share of x1 to xm that they obtain to the client. The client just retrieves the output of the function by just reconstructing the shares and applying function f locally, right? We don't want that to happen. So we want the last round message from the servers to the clients to only grow with the size of the output. Okay, so this is what is called as a secure computation protocol. So any questions about this before we proceed?
I think you're good to.
Yeah, okay. So the result that we are going to see today is that of Benor, Goldwasser and Wigderson from 1988, where they showed that if the number of cloud service providers that you are sharing to is greater than or equal to 2t plus 1, okay, where t is the number of corruptions that your protocol can tolerate, then for any function f, there is a protocol pi that securely computes f against t server corruption. So this result seems mind-boggling, right? For any function f, as long as the number of cloud service providers is greater than or equal to 2t plus 1, there is a protocol that can securely compute this function. against T server corruptions. Okay, so this is the result that we are going to see today. Okay, so let's see how to construct such a protocol. Okay, so how is this function f described? So let me first get to this point. So the function f is described as a sequence of instructions. Okay, so instruction 1, instruction 2, and so on. So what is the input to this function? It's the secret data of the client, x1 up to xn, right? So there are m secret data, and the client just stores them on the server. The function has to operate on these secret data. So the instruction, each of these instructions is the following form. So you take a register R1, okay, so what does it do? So it first stores x1 to xn on registers R1 up to Rn. So okay, so it has some set of registers. It just copies x1 to xn to these registers R1 to Rn. So the instruction 1, it takes R1, okay, so Rm plus 1. Okay, what it does is that it gives you two registers Ri, Rj for I comma j less than or equal to n, and it asks whether you just add these two registers and store it on Rm plus 1, or you multiply these two registers and store it on Rm plus 1. Okay, so there are just two basic operations that you want to support, just additions and multiplications on these values. So you just add those two, any two registers, store it on Rm plus 1, or multiply any two registers, store it on Rm plus 1. This is the first instruction. Second instruction is just again Rm plus 2, you have Ri, Rj, again you can just add or multiply, and these operate on any registers I comma j less than or equal to m plus 1, and so on. Okay, so each of these instructions is just, think of just doing some operations on the input values, storing all the intermediate values in registers, and then computing on the other registers on the intermediate values or the input values and so on. So this is the set of computations that are being happened. Okay, so you can in fact show that even if you are so if there are some other registers that store, let's say, the constants r prime 1, which just stores the -1, and r prime 1, which just stores 1, then any function can be described as in this language, meaning that you just operate on the set of registers, and you just add two registers, store it in a new register, or multiply two registers and store it in another register, and so on. Okay, so you can actually describe any function in this particular language. Okay, so for those who are familiar with the notion of arithmetic circuits over some finite fields, this is just an arithmetic circuit. So this is all that you want to do. This is how I want to represent a function in terms of this particular register-based language. Okay, so any function f can be translated to this particular language. Okay, so now given this, this function description of this function in this particular language, let's see how to compute this function via this protocol. How do you describe a protocol that computes this function against T server corruptions? Okay, so the first step is, of course, the input sharing phase, where you have these x1 up to xn, right? You just secret share x1 to xn using Shamir secret sharing. That is, you just use a t plus 1 out of n secret sharing to get the set of shares sh1 up to shn for each of these x1 to xn. So you just share each xi independently using a Shamir secret share. Okay, So this is what is being stored on the cloud, right? Now the second step is to compute some function f on the cloud, right? So how do you do this? So these cloud service providers are going to jointly compute this function f. Okay, so I'll call these cloud service providers as the parties in the computation protocol, and they are going to jointly do this computation f. How does this joint computation happen? So for every, say for every instruction, okay, so there is the output of this particular instruction is stored on a registered value, right? Which is for every instruction I, the register value that is holding the output of this instruction is Rm plus I, right? So for this particular value that is stored in Rm plus I, that the invariant that this protocol is going to maintain is that the parties are going to hold t plus 1 out of n secret sharing of this value. Okay. So this is what we want to maintain. That is, for every register value that is being operated on, we want to ensure that the parties hold a t plus 1 out of n secret sharing of this value. Suppose we somehow maintain this invariant, then the protocol becomes trivial, right? So the output of this functionality is also stored on some registers. And since the parties or the servers in this case hold a t plus 1 out of n secret sharing of these output registers, what they can do is just to send these output registers to the client, the secret shares of this output registers to the client. The client can just reconstruct it and get the value of the output. Okay, so the main property that we want to ensure is how do we maintain this invariant? That is, for every registered value that is being operated on by this function f, we want to ensure that the parties hold a t plus 1 out of n secret sharing of this value. Okay, so this we are going to do by induction. So what is the base case? The base case is just the input wires. Right? How are the input, the input registers? Sorry. So how are the input registers stored? Input registers are stored by the client as a t plus 1 out of n secret share, right? This was the input sharing phase that was happening. So just by the way that the input sharing happened, the input registers are already stored in t plus 1 out of n secret shared form. Okay, so what about the induction hypothesis? So let's assume that all registers that are operated on by the first D instructions. So the first maintain the invariant, meaning that all the stored values on these registers are in t plus 1 out of n secret shared form. Okay, so what do you need to do is to show this induction step, right? So you need to show that even for the d plus 1th instruction, okay, you can actually maintain this invariant. Okay, so let's say that the d plus 1th instruction takes in two registers u and v and stores the output on w. So what was the instruction that, what could the instruction do? It could either just add u plus v, store it on w, or multiply u and v and store it on w, right? So by induction hypothesis, both u and v are already in t plus 1 out of n secret shared form. We want to ensure that w is also stored in t plus 1 out of n secret shared form. Okay, so let's see how to do this. let's start with the case where the instruction was just an addition. Okay, so now how do we maintain this invariant? So what do we have? We have u, which is stored in u1 to un as a t plus 1 out of n secret sharing of u, and similarly v, which is v1 up to vn, which is again stored as a t plus 1 out of n secret sharing of v. So now the goal is to get a t plus 1 out of n secret sharing of w, which is just u plus v. So how do we do this?
We can just use the fact that adding two polynomials will give the another secret sharing.
Right, exactly. So this is where we'll use the first useful property of Shamir's secret sharing. That is, if the server, if the parties just locally add the shares u1 v1, u2 v2, and un vn. Okay, so what do I mean by the value u is stored in t plus 1 out of n secret shared form? This means that the first party has u1, second party has u2, the nth party has un, and u1, u2, u up to un are a t plus 1 out of n secret sharing of u. Similarly, it holds for the case of v as well. Okay, so in order for the parties to generate a t plus 1 out of n secret sharing of w, what they can do is that they can just locally add their shares of u and v, and they can actually get a t plus 1 out of n secret sharing of w, which is just u plus v. Okay, so for the case of addition gate, we saw how to maintain this invariant. So the interesting aspect is how to do it for the multiplication gate. Okay, so w is just u times v, u product v, and so u1 to un is a t plus 1 out of n secret sharing of u, and similarly v1 up to vn is a t plus 1 out of n secret sharing of v. So how do we compute a t plus 1 out of n secret sharing of u times v? So what was the second useful property about Shamir's secret sharing that we saw?
Multiplying two secrets will give a new secret.
Yeah, but what was the problem with that approach?
It was becoming 2t out of.
Exactly, right? So if you just locally multiply the shares u1 v1, u2 v2 up to un vn, then what will you get is a 2t plus 1 out of n secret sharing of u times v, which is double. But what was the invariant that we wanted to maintain? We wanted to ensure that we actually get a t plus 1 out of n secret sharing of w rather than a 2t plus 1 secret sharing. Right? So the next step that we want to do is that of degree reduction. Okay, so what we have is a polynomial p that is actually a degree 2t polynomial where the constant term is w. Right? So what we want to ensure is to transform this degree 2t polynomial to a degree t polynomial with the same constant term. Okay, so if we are somehow able to do this, then we will be able to maintain this invariant. How much time do I have?
Maybe 10 minutes more.
Okay, so if there are 10 minutes, then it's fine. Okay. Okay, so the main the next step of this protocol is how do we do this degree reduction? That is, we have a polynomial that is of degree 2t. Okay, so the parties hold the evaluations of this polynomial at endpoints. Okay, but the polynomial is of degree 2t. But what we want to ensure is that we want to convert this polynomial to a degree t polynomial with the same constant term. Okay, so the constant term of this degree 2t polynomial is w, which is u times v. We want to convert this into a degree t polynomial that has the same constant term, which is w. Okay, so this is the degree reduction step. Okay, so I'll have time to go over the crucial aspect of the degree reduction step. There's one aspect that might not have time to cover, but I'll point out some useful resources where you can find the particular step. Okay, so what is the degree reduction step do? Okay, so there are n parties or servers, right? And they have a polynomial p, which is of degree 2t, right? And the parties hold the evaluations of this polynomial at alpha 1, alpha 2, up to alpha n, right? So we want to convert this to another polynomial cube of degree t, right? Such that q of 0 is same as p of 0, that is, both have the same constant term, and the parties now need to hold q of alpha 1 up to q of alpha n. Right? So this is the main problem of the degree reduction step. And so in order to solve this, so let's say that the parties magically get hold of this following two things. Okay, so the parties get hold of R1 of alpha 1 to R1 of alpha n, okay, for some polynomial R1, where R1 is a degree t polynomial. Okay, they also get R2 of alpha 1 up to R2 of alpha n, where R2 is a degree 2t polynomial. Okay, and R2 of 0 is same as R1 of 0. And this is just a random element from ZP. Okay, so what do the parties now get? So let's ignore for now how the parties can get this particular polynomials, but let's say that somehow magically they get evaluations of two polynomials R1 and R2, where R1 is a degree t polynomial, R2 is a degree 2t polynomial, with the important property is that the constant terms in both these polynomials is the same, and this constant term is just a random element, which is not known to any one of these parties. Okay, so suppose the parties can get such evaluations of two random polynomials. Now, how can they do the degree reduction step? Okay, so let me explain that. Okay, so what is the degree of polynomial p? It's 2t, right? So now what the parties do is that the parties just locally subtract p of alpha 1 from R2 of alpha 1, p of alpha 2, p of alpha 2 from R2 of alpha 2, and so on. So the first party just subtracts the evaluation of p from evaluation of R2 that it obtained. Second party subtracts the evaluation of p from the evaluation of R2 that it obtained, and so on. 2 of alpha n. So what can you say about the constant term of the polynomial p minus r2? It is just uv minus, let me call this random element to be r. It's just uv minus r, right? Because p is a degree 2t polynomial, r2 is also degree 2t polynomial. So p minus r2 is a degree 2t polynomial whose constant term is uv minus r. Okay, so the parties can just exchange these shares together and reconstruct uv minus r. Since r is just random, it does not reveal any information about u times v. Okay, so even if the parties know uv minus r, they don't get any information about uv, which is something that we wanted to ensure, because we wanted to ensure that the parties only learn a secret sharing of u times v rather than the individual value. Right? So once they get hold of uv minus r, they also have the polynomial r1, which is just this evaluation, which is just a degree t polynomial whose constant term is r, right? So now, so once parties get uv minus r, if they just add r1 of alpha 1, r2 of alpha, sorry, r1 of alpha 2. So what is this comprised of? This is just a degree t polynomial. What is the constant term of this polynomial? It's uv. Right? Okay, so this is how you do this degree reduction step. Okay, so I wouldn't have time to go over how the parties could get these random polynomials, but it's not too hard. So yeah, if you're interested, contact me and I'll be happy to share the details of how to generate them and so on. Okay, so yeah, that's all that I wanted to say for this talk. So yeah, so just to conclude, whatever we covered today was secret sharing and secure computation. There's a lot more to these two areas, and yeah, if you're interested in knowing more, yeah, feel free to contact me on my email and be happy to provide pointers to various other materials and so on. Yeah, that's it. Thank you.
Thank you, Professor, for this wonderful and beautiful lecture. And it was so simple to follow from the basic definitions and like even the secret sharing with just like very simple applications of polynomial and this multi-party computation. It was really wonderful, and I hope that everyone got to learn something new today. So if you have any questions, you can ask the professor right now, or even if you can go back later on and you can email us or to the professor, and we will be happy to get them answered. So there was one question in the chat related to this degree reduction. So it was that like when you define the product of two secret sharing the polynomials, we wanted the polynomial to be random, but once you multiplied these two polynomials, they were no longer random polynomial because
Exactly, right. So that's why we wanted to inject new randomness to it, and that's the goal. That's that's precisely the role that R1 and R2 are playing. So since we wanted it to be a random polynomial that has the same constant term, in order to ensure secrecy, we want to inject new randomness to this degree reduction step, and that's precisely the role of R1 and R2.
So there is one question in the chat about any recommended resources to follow up on this topic.
Yeah, there are a lot of sources. So Yeah. So there is so this degree reduction step that I just described is from a paper in 2007 by Damgard and Nielsen. I think it's Crypto 2007. But there is, if you want to learn more about secret sharing and the secure multi-party computation in this so-called information theoretic setting, you allow T corruptions, but you want the number of parties to be more than 2T plus 1. There is this very nice paper of Ashraf and Lindell. So this I think is it's called as a full proof security BGW protocol. So if you just search on the internet, just typing on full proof of security of BGW. BGW is the short form of Benor, Goldwasser, and Victorson. Then you can get the complete proof of security and so on. Yeah, I'll encourage you to look into this. So if to learn more about secure computation and so
on. And there is another question about any book for the beginners to start up with multi-party computations and secret sharing.
So there are some books which, but I'll encourage you to look into any good lecture notes to just get into secure multi-party computation. So there is this book by Oded Goldreich called Foundations of Cryptography, Volume 1 and Volume 2. I think secure multi-party computation appears in Volume 2 of Oded Goldreich's book. So you can just you can look into that for precise treatment of secure multi-party computations.
So I think now we can conclude this session. So thank you, Professor, once again for accepting our invitation and taking your time to give a beautiful lecture to this lovely audience. So we will meet tomorrow at 11 o'clock for the next talk by Professor Suresh Nayak on factorizations and polynomials. So hope to see all of you tomorrow. Thank you, Professor, once again.
Yeah, thank you.